Okay, good morning, everyone. Welcome back to Math 115. So today we are going to talk about sections 1.1 and 1.2 from the book. So we've finally finished the review. The review took a long time, but we made it through. So everything that we have done up until now, hang on, let me mark you here. Everything that we've done up until now is material which is covered in a little bit more detail in Math 111. So the placement test is okay at telling people what class they need to be in. But if you are wondering, is this class right for me? I feel like I'm behind. The review didn't feel much like review to me. Then you don't necessarily have to make that decision on your own. You can come and talk with me during office hours or something, or you can send me an email and we can find a time to meet on Microsoft Teams, and we can talk through, and I can give you a better assessment of whether I think you're well prepared for the class, and I can give you the best advice that I possibly can in terms of whether you should drop down to 111, or maybe if you're feeling like, oh, this is super boring and you want to go to 141, then we can talk about that as well. So, speaking of office hours, my office hours this week are supposed to be in person today and on Thursday in LeConte 439 from 2:30 to 4. So, I still have to actually go to LeConte and check my office. I'm doing that right after class today. I don't know what the status of the LeConte building is, but I'm hoping it's ready for us to have office hours in there today. If not, I'll send everyone an email. So be on the lookout. If you plan on coming to office hours today, I may send an email that we might have to do one more online office hours today, but we'll see. I'm hoping we can do it in person. Okay, what else? You had a few homework assessments that were due, I think, yesterday. Homework 1.1 I haven't posted yet. Well, it's on there, but I still have to clean it a little bit by removing some of the questions. So I'm going to remove a couple of the questions, and then I'll post homework 1.1. It'll be due on Wednesday. We're going to finish 1.1 today. Okay. Wait, today's Tuesday, isn't it? Maybe I'll make it due Thursday. That would probably be smarter. And since it's Tuesday, I'll probably remove 1.1 from the quiz that we're going to have on Thursday. Okay, so the next quiz is going to be this Thursday, and that's going to be covering sections A.4, A.6, and A.7. So we skipped A.5. We didn't do A.5 because that was geometry, and we're just not going to do much geometry this semester. All right, I think that's the announcements I have for you all. Does anyone have an administrative question for me before we start on content? Could I have a show of hands? Is anybody planning on coming to office hours today in LeConte with me? Sweet, a few people. All right. Oh yeah, somebody asked me the other day, would it be annoying if I came to every single office hours for the entire hour and a half? And I said, absolutely not. I would love for you to come to my office hours every single office hour for the entire time, and we can just knock out basically your entire homework assignment every time that you come, and I will help you with that. It's really not a problem. I want you guys to feel comfortable coming to my office hours because that is going to be a massive help for you all to learn a little bit better and for me to communicate some stuff that I don't have time to talk about in class. All right, well, it doesn't seem like there's any questions, so let's move right into content. Before we go into 1.1, let me remind you what we talked about last time. In A.7, we talked about a lot of stuff, a ton of inequalities. Okay, so we had, first of all, the properties of various inequality signs, and then we talked about solving inequalities. So we solved a few different types. Linear inequalities were very easy, relative at least as it compares to compound inequalities, where the OR had to correspond to a union in our solution set, and then the AND had to correspond to an intersection in our solution set. Okay, so we practiced graphing those and finding the solution set. And then we talked about the test point method. And the test point method was good for anything more complicated than a quadratic, basically. So if we have a quadratic or more complicated, we like using the test point method. We graph first where is the inequality going to be solved. In other words, when is it going to be solved as an equality? Those are the points which we put on our number line. So those ones are here and here, respectively. And then what we do is we have divided the real number line into 3 regions. We pick a test point from each region, and we check whether the inequality is true for that test point from that region. If the inequality is true for that test point, then we know that the inequality must be true for all of the points which are in that subregion of the real line. So that was the test point method, and it was great for quadratics, and then it's also great for the rational inequalities, which I really made a mess of this last time in class, but we made it through eventually. The goal is, of course, again, to find out where are we going to have an equality. To find out where we're going to have an equality, we had to multiply over and solve this quadratic. And then this is where we found out where does this rational inequality become an equality. Then we divided the plane, or the real number line, with those 2 points, and we picked a test point from each subregion. Of course, there was one other thing that we had to keep in mind, which was that this denominator can never become 0. So we also had to put on our number line a 3rd point, which was the point 1. So this divided our real number line into not 3, but 1, 2, 3, 4 subregions. And we had to pick a test point from each of those and plug back into the original inequality to see if all of the points in that subregion satisfy the inequality or fail to satisfy that inequality. So this was the most complicated one by far. And then the last thing we talked about was inequalities with absolute value. So the only trick with absolute value is we need to remember that the absolute value function, it does one of 2 things. If the number inside is positive, it does nothing, and we can just not write the absolute value sign. However, if the number inside is negative, what am I going to do to whatever is inside my absolute value? If I take an absolute value of a number, and that number is negative, what am I going to do? I'm going to make it positive. How do I take a negative number and make it positive using a mathematical operation? Very good. We're going to take whatever is inside and multiply by -1. In this case, we had x minus 7. So when we multiplied by -1, we had to distribute, right? So when we distribute -1 onto x minus 7, we actually got 7 minus x. Okay, that's probably too small for you all to see. 7 minus x was what we got when we multiplied by -1. Okay, so before we move on to new material, any questions on this last bit of review that we finished up last Thursday? Okay. If not, then let's get right into 1.1. So chapter 1, we are going to learn some basic things about equations and graphs and functions, where, a key component of this is relating 2 unknown quantities x and y, right? A big part of that is relating 2 unknown quantities x and y, which is why René Descartes back in the day invented this heuristic, I guess, for visualizing a relationship between 2 numbers. So what he did was he said, well, I have the real number line going left to right. What if I just did another one that went up and down? Okay, so that's what he did, and he made this thing which we now call the coordinate plane or the Cartesian plane. And you can see that on the x-axis, Negative is to the left, and positive is to the right. Okay, that makes sense. We've already seen that. And the way we do the y-axis is that positive goes up and negative goes down. Okay, so this is how we are going to graph something which is called an ordered pair. So an ordered pair refers to something which looks like A comma B with parentheses here, okay? Now there's a big difference between an ordered pair and an interval, okay? When we're talking about an ordered pair and an interval, they look the same, right? They look the same. But for an ordered pair, it's understood that the first number refers to the x-coordinate and the second number refers to the y-coordinate. So it will always be specified whether we're talking about an ordered pair here or an interval. Well, in this case, or in a lot of cases, it's actually not going to be specified. It's going to be indirectly specified by the context of the problem. Okay, so if you're talking about a coordinate plane and you see something like this, you should probably think we're talking about an ordered pair here. Okay, so the way we graph it is pretty simple. We go to the x-coordinate, which is specified by the left thing, and then we go to the y-coordinate, which is specified by the right thing. So in this case, 3 is the x-coordinate, so I need to go 1, 2, 3 units to the right. Okay, and how about -2? -2 is the y-coordinate, so what should I also do? In addition to moving 3 coordinates to the right, I should move also 2 units down. So 1, 2. So that's -1, that's -2. This is 1, 2, 3. So our point is going to be right at the point where those two meet. Okay? So 3 on the x-axis and -2 on the y-axis. So that's how we graph a point in the coordinate plane. Okay, and now this is sort of looking like a map, right? This is looking kind of like a map where, you know, if I were to put this down on a table and show you, okay, I am here, I want you to go here, then what we would do if we wanted to know how far you would need to go is we would measure the length of this line segment, right? So let's see how we do that really quickly. So we already defined the distance between points on the real number line, right? It was just the absolute value of the difference of those points. But now an ordered pair has two entries, right? So it's a little more complicated than just subtracting stuff. So what do we have to do? What we have to do is first recall the Pythagorean theorem. So let's do that now. Well, the Pythagorean theorem says if I have a right... Okay, I don't need that. If I have a right triangle, and the side lengths, which are not the hypotenuse, so first of all, let me label. This is the hypotenuse, is what we refer to as this side of this triangle. Okay, it's opposite of the 90-degree angle. All right, if that side length has length A and this side length has length B, then what is the side length C going to be? How do we relate A, B, and C? We have an equation, the good old Pythagorean theorem. Yeah, Carter?
A squared plus B squared.
Yeah, it's C squared equals A squared plus B squared, right? So if C squared is A squared plus B squared, and I want to know what is C, well, C is going to be equal to what? The square root of A squared plus B squared. Okay, so that's the Pythagorean theorem. It works for triangles that have a 90-degree angle. Okay, so why is this triangle business helpful for determining the distance between 2 points on the coordinate plane? Why is this helpful?
You can go with like triangle shapes.
Yeah, I can draw a triangle here in the following way. I can draw two legs of the triangle, one of which goes only left and right, and one of which goes only up and down. I do it in the following method, okay? First, I'll draw the one that goes up and down. It goes like this. And then the one that goes side to side, it goes like this. And you know that two lines which are perpendicular form a 90-degree angle, right? So now all of a sudden we have a right triangle. And we can use the Pythagorean theorem because it's easy to measure these two distances. Why is it easy to measure these two distances? Because we already have the distance function for determining the distance between 2 points on a number line, right? And if we go in just the left and right direction or just the up and down direction, we're just moving up and down on a number line. So since we already learned how to find those distances, and we know that we can find this distance as a function of the other two, we're in business for finding the distance between 2 points. Okay, so let's see how that works. So let's say I have a coordinate plane, and I'm going to refer to 2 points. Okay, I'm going to refer to 2 points, x1, y1 is going to be this point right here. In fact, why don't I move it down here? And then x2, y2 will be this point here. Okay, so what we need to do is understand our special triangle here. It's going to look like this, right? It's going to look like that. And let me draw this out a little further. Okay, and then here we go. To finish it off. So, this is our goal. This is what we want to know. What is the length of that hypotenuse there? So how should I figure out the length of this side? Well, it's as easy as looking at the y-coordinates, right? It's as easy as looking at the y-coordinates, right? So this length here is just y2 minus y1 in absolute value, right? And then the other length on the other side is x2 minus x1 in absolute value. Why do I use absolute value? Because it works even if I were to switch these two, right? If I were to do y1 minus y2, I still get the same answer. Okay, so then we want to figure out what is the question mark. Well, we know that the question mark is going to be equal to the square root of x2 minus x1 in absolute value squared plus y2 minus y1 in absolute value squared. Okay, except guess what? If I take a number and I square it, okay, if that number was negative or positive, I still get the same result. You agree with me there? If I take a negative number or a positive number of the same absolute value, I get the same result. So I actually don't need these absolute value signs. So absolute value signs are, let's use a real big word here, superfluous, meaning that they're extra and unneeded. Okay, so let's now define this distance function as follows. The distance between 2 points on the coordinate plane, if one of them has form x1, y1, the other one has x2, y2, what do? We take the square root of x2 minus x1, quantity squared, plus y2 minus y1, quantity squared. And the nice thing about this function, or this distance measurement, is that it doesn't matter what order we put the points in. Okay, why doesn't it matter? It doesn't matter because if I do x2 minus x1, I'll get a number. So if I do x2 minus x1, I will get a number. If I do x1 minus x2, what will I get? I will get that same number, but negative, right? And we already agreed that if I have one number and then the same number but negative, and I square it, I get the same thing, right? So this works no matter what order we put the points in. Questions on the distance measurement? Okay. In that case, let's talk about the midpoint. Okay. Well, maybe it would be easier to talk about first on the real number line. If we talk about on the real number line, how do I find the halfway point between x1 and x2 on the real number line? How do I find the halfway point between these two?
Subtract x2, x1.
If I subtract x1 from x2, then I will get the distance between x2 and x1, right? So I have the distance between them. Okay, so now I divide by 2. Okay, so now what do I have? I have a measurement of halfway between them. This distance here is what this is, right? How does that help us? So what do I do with this distance in order to get this point here? What I need to do is I need to take that distance and add it to x1, right? If I take this distance, which is shown in red, and I add it to x1, then I will get the point x3, which is the midpoint, right? Now let's simplify this. If I were to take this and simplify it, what would I get? Well, I'd put x1, I'd make it into 2x1 over 2, right? So this would become times 2, divide by 2, and I'd add, so I would get x2 minus x1 plus 2x1 over 2, and I'd get x1 plus x2 over 2. Okay, so this is how I can find the midpoint between 2 points on the real number line. In other words, the halfway point between two numbers is the average of those two numbers, right? The halfway point between two numbers is the average of those two numbers. Okay, the only thing that's going to be different when I do this in the Cartesian plane is I'm going to do it twice. Okay, so let's say midpoint between, I'm going to erase this. We're going to do midpoint, oh, I see what this is. Oh, this is confusing. Why don't I say this is m of x1, y1 and x2, y2. The midpoint is going to be equal to x1 plus x2 divided by 2. I average the x coordinates, and then I do the same thing for the y coordinates. y1 plus y2 divided by 2. So visually, what does this look like? Let me show you. So, okay, if we have x1 here and this should be y1. y1 here and y2 here, and we have x1 here, and then we have x2 here. So our 2 points are here and here, respectively. My goal is to draw a line through these 2 points, and I want to find this point here. Well, the way I find the coordinates of this point is by finding the midpoint between both of these segments. So I take this segment, I take the midpoint. That's how I find this value. And then I take this segment and I take the midpoint, and that's how I get the x value, right? So this is how I find the midpoint for between 2 points is I take the average of the x coordinates and then the average of the y coordinates, and I use those to form my new point. Any questions on distance and midpoint before we have a chance to practice? Yes, Andrew.
Can you go over an example with real numbers?
Sure, I could go over an example with real numbers. Okay, I was planning on doing partner work here to try to apply these formulas, but let's have a class vote. We'll have a vote between doing this as partners or I'll show it as an example. Who votes to work with partners to try this one out before I show it? Wow. Okay, a few people. But who says let's work it out as an example together? Everyone, almost. Okay, we'll do that then. If you want to have some more practice with this on your own, then you'll just have to come to office hours or send me an email and make an appointment. Okay, so let's see how this works. Well, let me just copy down the relevant formulas into the relevant spots. So this was the distance formula. I'm going to copy it here. And I'm going to paste it here. Okay, and this is the midpoint one, so I'll also copy down the midpoint formula, which was given by here. So, I mean, you can memorize these if you want. I think it's also probably easier to just not memorize the formula, but just rederive it when you need it. So just remember, okay, well, how do I find the distance between these 2 points? Well, oh yeah, I can draw that triangle, and then Pythagorean theorem, what is this distance, what is that distance, square them, add them, take the square root. Okay, now I've got it, right? That, I think, is probably easier than memorizing these formulas, but if you want to, you're more than welcome to just memorize them. Okay, so let's find the distance between 2 points which have numbers this time. Okay, -1, -1, and 2, 3. So let's draw a picture first. I think that's always helpful to draw a picture first. Where's the point -1, -1? Well, if I were to label these quadrants as the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant, which quadrant do we think that -1, -1 is going to live in? It's going to be in quadrant 3. Very good. So it's here. -1, -1. Okay, how about 2, 3? Quadrant 1. Very good. So I go over 2 and up 3. So these are the 2 points. And my goal right now is to find the distance between them. Right? This is what I want to know. And the way I figure it out is by looking at this triangle. Right? And then this distance here is x2 minus x1, and this distance, it's y2 minus y1. And this is x2 minus x1, right? In absolute value. So, okay, what's my x1 and y1? Right here. What's my x2 and y2? Right here. So all I do is I'm going to plug directly into the formula. I get the square root of x2 minus x1, that's 2 minus -1, quantity squared, plus y2 minus y1, that's 3 minus -1, quantity squared, which is the same as the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, which is the square root of 25, which is 5. Okay, so how did I do that? Well, I just looked at the side lengths of this triangle, right? I know that this point here is at -1. So to go from this point up to this point, in terms of verticality, I need to go from -1 to 0 to 1. Oops. So yeah, -1 to 0 to 1 to 2 to 3. That's a total move of 4, right? How about left to right? I need to go from -1 to 0 to 1 to 2. That's a total move of 1, 2, 3. So that was how I got that this side length is 3, this side length is 4, and of course, if you know that this is a 3, 4, 5 triangle, then the other side has to have length 5. But you can also learn that through the Pythagorean theorem if you forgot about 3, 4, 5 triangles. Okay, so it's as simple as this number goes here, this number goes here, this number goes here, and this number goes here. Okay, so if you've got the formula, you just plug and chug. Any questions on the distance problem? Yeah, if you memorize the formula, then you really don't need to draw a picture, do you? You can just plug right in. That's fine if you want to do it that way. Okay, let's see the midpoint then. Well, to do the midpoint, again, all I'm going to do, this time I'll do it without a picture. Or maybe I'll draw the picture after. But the first thing I'm going to do is I'm going to recognize this is x1, y1, this is x2, y2. Or if you want to do x2, y2, and then x1, y1, go ahead. It's still going to work. Okay, because the average of -1 and 2 is the same as the average of 2 and -1. Right? So, okay, let's just plug it in. So let me draw exactly where these are going. x1 is going right here. x2 is going right here. y1 is going right here. And y2 is going right here. So let's go ahead and plug in. I get -1 plus 2 divided by 2. And then on the second one, I get -1 plus 3 divided by 2. Now I'm going to simplify. I get 1/2, comma, 2/2. Right? 1/2, comma, 2/2, which 2/2 is just 1. Okay, great. So let's see how that works on the coordinate plane really quickly. Okay, so we have a coordinate plane here. What do we have? -1, and 2, 3. Okay, so let's draw it nicely. This is our first point, and then we've got our second point here. Okay, so our goal in this problem is we look at the line segment between, and we want to find the point that's right in the middle. It's right in the middle. So what do? We take this line segment and we find the center of it by taking the average of the right endpoint, which is 2, and the left endpoint, which is -1. So the average of 2 and -1 is we do -1 plus 2 divide by 2, and we get 1/2, right? So that was how we found out what this x value is. So this is 1/2. So this point has the form 1/2, comma, and then to find the y value, what did we do? We took this line segment and we found the midpoint by taking the average of -1 and 3. So we add -1 plus 3, divide by 2, and we get 1. So that's how we found out that 1 was the midpoint of the vertical segment. Okay? And we combine those two together to get 1/2, comma 1, which are the coordinates of this point, which is exactly halfway in between the 2 points which I started with. Okay, so again, there's a very, very, very visual and like geometric interpretation of what we're doing here. It's basically taking averages, but if you say, screw that, I don't want to know about no averages, I just want to memorize the formula, go ahead. That's also fine. But I think it's harder that way. All right, any questions on the example where we did this with real numbers this time? We did the distance here using the Pythagorean theorem or the distance formula, and then we did the midpoint using the midpoint formula. Let's have some thumbs. How do we feel about these two so far? Thumbs straight up if you feel great, down if you feel bad, and somewhere in between if you're somewhere in between. Okay, I think most people are thumbs up, so I'm going to move on. So we're going to talk about section 1.2 now. So new section here. Okay, new section. Before we go to the new section, I'm going to really quickly actually go back and emphasize something that I was talking about here, which I mentioned offhandedly. Okay, when I say quadrant 1, 2, 3, and 4, I'm referring to 1/4 of the coordinate plane. So this quarter, which I'll shade in with red, we call that the first quadrant. This one we call the second quadrant, and we go around counterclockwise. So here's 1, here's 2, and then the third quadrant is down here. Oops. The third quadrant is down there, and then the fourth quadrant is in the bottom right. Okay, so that's quadrants of the coordinate plane. By the way, does anybody know what René Descartes is famous for? Maybe more famous for than he is for the Cartesian plane?
He's a scientific revolution thinker.
Yes, but in terms of maybe a famous quote?
Oh, I think therefore I am.
That's right, Andrew's got it. Descartes was a interesting guy. He was what's called a polymath, which back in the day, people didn't specialize like we specialize now in terms of I only do math or I only do chemistry. He was like, I'm going to do everything and be like a genius at everything. And so he was doing math. The other thing he's really famous for is philosophy. So cogito ergo sum, I think therefore I am, was something that he had invented while he was doing a thought experiment. He was trying to understand the theory of knowledge, or how we know things, or what can we say that we know for sure. And well, he thought, well, it's possible that right now I'm dreaming and all of my reality is completely imagined, right? All of my reality is completely imagined. So what's the one thing that I can know for sure is that I am having a conscious experience right now. That's the one thing that is undeniable. So that's why he said, I think, therefore I am. Anyways, this isn't Philosophy 101. This is Math 115, so we'll get back to it. Okay, so let's talk about graphs. So far we talked about the Cartesian plane, and now we're going to build the things which are going to live inside of our Cartesian plane. And the things that live inside of our Cartesian plane are, we've already seen points. Okay, so we've already seen ordered pairs. But now we're also going to see the graph of an equation. And later we're going to see the graph of a function. Okay, but let's see the graph of an equation first, and let's define it. So the graph of an equation, okay, the graph of an equation. So here's an equation, something like y equals x squared. What is going to go on the graph? It's going to be the collection of all ordered pairs, x, y, such that if I plug x in for x and I plug y in for y, then this equation is satisfied. Namely, I get something true. Okay? So let's see a quick example. We'll do the graph of y equals x squared. Does anybody know what the graph of y equals x squared looks like? Yeah, it's a parabola. But let's say that we didn't know that the graph of y equals x squared is a parabola. And we wanted to understand whether or not the point 1, 1 should go on the graph. So here's the point 1, 1. We want to know, is it a part of the graph of this equation? Well, what do? We just take it and we plug it in. So I would do 1 squared, I'd do 1 for the y, and then equals to 1 squared, for that's where I put the x, right? So the y goes here and the x goes here, and we plug it in, and we get 1 equals 1. True statement? Yes. This is true, therefore it is on the graph of this equation. How about 3, 3? Let's try it. 3 is equal to 3 squared. We get 3 is equal to 9, which is false, right? So therefore, 3 is not on the graph of this equation. Okay? So if you want to know how to sketch the general shape of this, you can just pick a few x values, by the way, and plug them in and see what you get. So if I plug in 0 for x, I get 0 squared is 0. If I plug in -1 for x, I get -1 times -1, which is +1. Plug in -2 and 2, I'm going to get the same thing. I'll get 4, right? Because I'll square those. And then, of course, this looks like our famous parabola. I didn't draw it very well, but you get the gist. Okay, so this is about the graph of an equation. when I talk about the graph, I'm talking about the collection of all points x, y. In fact, it's the set of all points x, y that satisfy the equation. So I've got another bucket. That's right. And what am I throwing into my bucket? All the ordered pairs that do satisfy the equation, and none of the ordered pairs that don't satisfy the equation. That's the graph. Any questions about how we determine whether a point is on the graph of a function or not? All right. So let's talk about intercepts then. Okay, so what are intercepts? So intercepts, okay, is the name we give to a subset of the points on a graph. Okay? We want to find just the points which cross the x-axis. Okay? Well, if a point on the graph is touching the x-axis, then you would agree with me, I hope, that that point has no vertical component. Right? If it's on the x-axis, then it has the form x, some x value, determines how far left and right we go, and then the y value should be 0. Agree? Okay, so this is how we find the x-intercepts. We look for points with the form x comma 0. And if it has that form, we call it an x-intercept. Sometimes we also call it a horizontal intercept. The reason I say horizontal intercept and not x-intercept is sometimes we do graphs of equations where this is the t-axis, or maybe it's the theta axis, right? So it might not necessarily be an x-axis, so we call it a horizontal intercept to refer to the fact that it's intercepting the horizontal axis, whatever that axis may be. Okay, the next one is, of course, we swap the roles, okay? If we make the x value 0 and we allow y to be whatever it wants, as long as it's on the graph, it is called a y-intercept. So really, I should actually say a point on the graph. A point on the graph. With this particular form. So we need two things. The point needs to be on the graph of the equation and have this form. So let's see how we actually find them. Any questions about the definitions before we talk about the method which we're going to use to find the intercepts? Okay, doesn't seem like it. So let's see what we do. Well, if we want to find the x-intercepts, we want to find all the points which are on the graph that have the form x comma 0. So what am I going to do? I'm going to take 0 and I'm going to plug it in for y, and I'm going to take x and plug it in for x, and then I'm going to solve and see if I can find all the values of x such that x comma 0 is on the graph. Well, let's see an example of that. So to find the x-intercepts, I'm going to plug 0 in for what? Y or x? Y. I'm going to plug 0 in for y to find the x-intercepts. It's a little confusing that way. Okay, what happens if I do that? I get in a quadratic equation, right? X squared minus x minus 2 is equal to 0. Okay, so let's factor. X, what do we get? Minus 2 and then plus 1 is equal to 0. So therefore, by the zero product property, we get x equals to 2 or x equals to negative 1. Okay, so what has this told us? This has told us that we have a quadratic equation here. What kind of shape does a quadratic equation have? It's another parabola. And does this one open up or down? Do we know if it looks like this or like this? How can we tell?
Is it up because there's not a negative sign?
Squares, if it's positive or negative.
Exactly. We need to look at the leading term. And coefficient on our leading term is positive. It's 1, right? That's A. So I look at A to figure out whether it opens up or down. If it's positive, we open up. If it's negative, we open down. So we know this is a parabola opening up, and the x-intercepts are 2 and -1. So here's -1, and here is 2. So we know we have a parabola which looks like so. And it's going to look probably something like the following, right? All right, let's do the y-intercepts. Well, to find the y-intercept, to find the x-intercept, I plug in 0 for y. To find the y-intercept, I plug in 0 for x. So we get y is equal to 0 squared minus 0 minus 2, which is -2. Okay, so we get another point. Here is -2. So we know that -2 is on the graph of this parabola. Okay, so these are the x and y intercepts. Okay, if you want to write them as a point, the points would be 2, 0, and -1, 0 for the x-intercepts. And then for the y-intercept, since the y value is -2, the x value is 0, it becomes the point 0, -2. So probably I would say these are going to be my like final answers for this in terms of x-ints and y-ints. Well, just one. Okay, and I can use that to help me draw this thing, right? I know that when I'm here, I haven't quite reached the bottom yet, right? Why not? Because I'm not halfway between these 2 points. The center, or the vertex of the parabola, is going to be halfway between -1 and 3, which we know happens at 1/2. So probably there's like another point here, or something like that, and our parabola probably looks something like shown. Okay, so -1, 0, that's this point, 2, 0, that's this point, and then 0, -2 is this point here. All right. So finding intercepts comes down to plugging in 0 for one of the variables and solving for the other variable. Let me ask you, what do you think is the most difficult or confusing part about finding x and y intercepts? What do you think is the most difficult or confusing part about finding intercepts? It's a qualitative question, really an opinion. Yep.
Will there be like a point where you have a problem and the x-intercept is going to end up being like a fraction?
So the question is it, well, it's certainly possible, but the question is, are we going to have a problem on a quiz or a homework where the x-intercept might be a fraction? The answer is yes. There probably will be. Maybe not on like a, I mean, it won't be like a really bad fraction. It could be something like 1/2. If it's a quiz and you don't have a calculator, I'm not going to give you like -135 over 137 or something crazy like that. But yeah, basic fractions are definitely something that you need to be able to do without a calculator for the purpose of the quiz and a test. Any other questions? Or the original question was, what's the hardest part about finding x-intercepts or y-intercepts, in your opinion? Or do you think it's just so easy that there is no hard part? Gavin?
I think it's all like relatively decent stuff. Just more like putting it all like cohesively together, make sure like everything works out overall.
Yeah, there's kind of a lot of steps, right? We got to plug in one thing, then solve, then plug in another thing, and then solve, and then write down the points. Okay, so it gets a little more complicated, right? I think, in my opinion, the hardest part of this is really simple. It's just that for me, when I'm doing x-intercepts, it's hard for me to remember that when I find the x-intercept, I need to plug in 0 for y. And then when I do the y-intercept, I need to plug in 0 for x. So those always get me confused because, like, when I'm not looking at the point, it's hard for me to remember, like, which one should be 0 again. So that is a really common thing that I see students make mistakes on a quiz or a test where they meant to be finding the x-intercepts, but they actually found the y-intercepts, or the other way around. So that's the tricky part. But I feel like it's helpful if you can remember that it's tricky, because then you'll be like, wait, I remember there was something weird about this. Let's think through it before I go. Yeah, by the way, I think that's a really helpful technique when you're doing the homework, or just any problem that will almost always help you to be able to solve it, is like when you're struggling with something, ask yourself, like, okay, what are the components of this problem and what is the part that I'm struggling with, right? I know if I could just do this, then I could simplify and get my answer. So like then you can identify, like, I'm struggling with completing this part of this type of problem. And that's the perfect thing which you could come to my office hours and tell me, and we could just work on a bunch of examples and help you get over that. So really helpful technique for learning math. Okay. Any questions on the intercepts before we move on? Okay, let's see what else do we have for today. Okay. All right, let's talk about symmetry really quickly. And I don't expect you to write all of this stuff down, by the way. What I just want to have it written out, and if you want to go back and check the notes, then you can check the notes. But for the symmetry here, I'm going to talk about 3 different types of symmetries of graph. So symmetric, if something is symmetric, that means it looks the same on one side as it looks on the other side. Okay, so, it's like a mirror image. Okay, so if you have a mirror image, then you can ask yourself, in what direction is the mirror oriented? Okay, in what direction is the mirror oriented? And then we can define 3 different types of symmetry. So the first type of symmetry I'm going to define is when a graph is called symmetric about the y-axis. Okay, about the y-axis. So what that generally means is that the graph is going to look the same on the left side of the y-axis as it does on the right side of the y-axis. So can someone give me an example of an equation that would be symmetric about the y-axis?
Y is equal to x squared.
Sure, we already saw one. Y is equal to x squared will be symmetric about the y-axis. Why? Because we satisfy this following condition. For every point x comma y on the graph, the point negative x comma y is also on the graph. Okay, so here's the point. Here is the point 2 comma 4. And what else is on the graph? We've also got negative 2 comma 4. Okay, so the point is that I need to be able to take any point that I want along the whole graph of this guy, anywhere. And I need to be able to also plug in the negative of that x value and get out the same height. That is symmetry about the y-axis. Okay, so the difference between symmetry about the y-axis and the x-axis is that when we're about the y-axis, we're symmetric left and right. When we're symmetric about the x-axis, we are symmetric up and down. So this time, we're going to have something like this kind of a symmetry. Okay, this kind of a symmetry. So can anybody give me an example of an equation which is going to be symmetric about the x-axis? So for every point above the x-axis, there's going to be a corresponding point below the x-axis with the same height but negative and same x value. Yeah, we could do x equals y squared. We could do x equals y squared. Then what is that going to look like? It's going to look like a parabola opening this direction, right? Oops. It's going to look like a parabola opening this way, right? So here's the point, 4 comma negative 2, and then this would be the point 4 comma 2, right? Because if the y value is 4, wait, what am I doing? No, the y value is 2, so 2 squared is 4. That's how we get the x value. And likewise, if we plug in negative 2 for y, we get the same thing for x. Okay, so this is symmetry about the x-axis. What we look for is any point that I pick, I can plug in the opposite y value and get the same x value. Okay. Lastly is for graphs which are symmetric about the origin, okay? And so this is kind of like we combine these two, and we take for every point x, y on the graph, the point negative x comma negative y is also on the graph. So what does this mean? It means if I have a point here, which is like 1 comma 1, what else do I need on here? I also need the point negative 1 comma 1 to be on the graph. Okay. Can anyone think of a graph which is symmetric about the origin, which passes through these 2 points? What kind of equation passes through these 2 points? You could do a straight line for sure, right? You could definitely do a straight line. How about y equals x? Okay, it's symmetric about the origin, which the origin is the point right at the crossing of the 2 coordinate axes, right? Okay, so another one that you could do is also something like y equals x cubed, right? What would y equals x cubed look like? It looks like this, kind of. All right, so these are the 3 types of symmetries that we can observe in a graph. And symmetries are helpful because if we can identify a certain type of symmetry, then it will help us to draw the graph, because we only have to draw half of it and then just copy that half over, right? Okay, so let's see, how do we test for x symmetry, y symmetry, and origin symmetry? Well, what we're going to do is use this definition. We want to check, is it true that if I take a point x, y, if I plug in the opposite x value, do I still get the same y value? That is our goal here. So our goal here is to test for x symmetry. We're going to replace y with negative y. Okay, so let's see if we have x symmetry for this equation. Well, what I'm going to do is I'm going to take negative y, okay? And I'm going to set that equal to 1 over x squared plus 5. And the question is, does y equals 1 over x squared plus 5 imply that negative y is also equal to 1 over x squared plus 5? And what do we think? Is this equation equivalent to this equation? Yes or no? Are these 2 equations equivalent to one another? I'm hearing some yes and some no from various people in the crowd. Well, let's see how we can maybe think about this. you agree with me that if y is positive, then negative y is negative, right? Fairly simple, right? So if this is a negative number, okay, let's ask ourselves, what kind of number is 1 over x squared plus 5? If x is a positive number, what kind of number is 1 over x squared plus 5? Positive. If x is a negative number, what kind of number is 1 over x squared plus 5? Still positive, right? So is there any number that I can plug in for x that's going to make this negative? Well, if I plug in -1, I'd get -1 times -1, which would be +1, and then I'd add 5, and I would end up with 1/6, right? So again, it's positive. So no matter what I plug in for x, it's always positive. So this is not possible. Okay. So these two equations are not equivalent. Okay, now let's test for y symmetry. Let's see what the table says to do. It says I should replace x with -x and see if I get the same thing. Well, if I do y equals 1 over x squared plus 5, the question is this the same as the equation y is equal to 1 over -x squared plus 5? What do we think? Are these two equations equivalent? They are equivalent. And why are they equivalent? They are equivalent because -x squared is the same thing as x squared, right? Let's try it. Is 2 squared the same as -2 squared? Yes, that's 4 is equal to 4. Right? So we know that if I take two negative numbers and multiply them together, I get the positive number, right? So these two are the same because I can simplify the right-hand side to be equal to 1 over x squared plus 5. And y equals 1 over x squared plus 5 is exactly what we had before. So we haven't changed anything. So we do have y symmetry. We do not have x symmetry. Okay, and then the last one, if we want to test for symmetry about the origin, what do? We switch both of them. We check if I take y equals 1 over x squared plus 5 versus negative y equals 1 over negative x quantity squared plus 5. Are they the same? Well, the right one we can simplify to negative y equals 1 over x squared plus 5, which again is impossible if y is positive. So again, this is a big no-no, so no origin symmetry. But generally, if you have one type of symmetry, you're not going to have any of the other types. Well, actually, that's not true. You could have a circle. Circle is symmetric in every direction, right? Okay, but generally, for the most part, you're only going to end up with one type of symmetry. Okay, so let's see what this graph actually looks like. Let's think about it. If I have 1 over y equals 1 over x squared plus 5. So what happens? Basically, I take whatever the x value is. Am I over yet? No, we got 10 minutes, right? We go to 45? Okay. So, okay, we got y equals 1 over x squared plus 5 here. So what do? We take whatever the x value is and square it and add it to 5. So the bigger the x value, as x gets bigger, what is going to happen to this number? Well, the denominator gets bigger. I should have said what happens to this total fraction. If the denominator gets bigger, then the number itself is getting smaller, right? So when is this going to be at a maximum? What's the largest value that this is going to take? When is that going to occur? Well, if I want to make this number as big as possible, I want to make the denominator as small as possible. So I want to make this x squared plus 5. When is x squared plus 5 the smallest? Is when x is equal to 0. So we're going to have a maximum at x is equal to 0 with 1/5, right? And then what's going to happen? The further out we go, x is getting bigger, so the denominator is getting bigger, so the entire fraction is getting smaller. It's going to look something like this. And it is symmetric about the y-axis. So I don't actually have to figure out what's happening on the other side, although it's not hard to see. I can just copy over what I have on the right side. So it looks something like this. Okay? All right. So are there any questions about the symmetry of graphs and how do we check for the symmetry of graphs?
No.
Thank you. Sometimes it takes people a little bit of time to work up the courage or to put their question into words. So I like to give a little bit of time. I know it's awkward sitting there while I'm just being silent, but all right, let's talk about the last thing for today then. Okay, so what we're going to talk about is the definition of a circle. Okay, so this section I feel like is all over the place. We got symmetry, we got, what the hell else did we have? X-intercepts and Y-intercepts and all sorts of stuff. And now, on top of that, we're going to randomly throw circles into the mix. I don't know why they do that, but they do. Okay, so we have a circle, which is defined to be the set of points which are equidistant from a given center. And we call the distance from the center the radius, right? So the point is that if I start at the center, I can walk in r feet in any direction. And the collection of the locations which I could travel to by traveling r feet in any direction is what we call the circle. So the circle itself is not the center, it's not the middle, it's just this collection of ordered pairs which I can get to by walking this far away from the center, which we call the center. We usually denote HK, where H is the X coordinate of the center and K is the Y coordinate of the center. So the standard form of the equation of a circle is what? Well, what we say is that if we were to draw a triangle in here, right? If we were to draw a triangle in here, okay, and let's say that we are on the coordinate plane. Then what has to be true? We need our points on this circle to be exactly r units away from the center. So what that means is that this distance and this distance have to satisfy the equation. If this is a and this is b, we need a squared plus b squared equals r squared, right? And how do we get a? Well, a is the difference in height between this point and the center of our circle, right? Which again is going to be whatever this y2 is. It's going to be y2 minus k, right? Or y minus k. So we take y minus k squared and we take x minus h squared. Those are going to be the lengths of these two sides of this triangle, and we want them to satisfy that the Pythagorean theorem where the radius goes on the other side. So we get x minus h squared plus y minus k squared is equal to r squared. That's how we get the collection of all points which are r units away from the center of our circle. Okay, so the terminology we use is we say that this is a circle with center HK and radius R. So let's see an example of how we would graph a circle if they gave it to us. And the trickiest thing for me about the circle is remembering that in the standard form of the equation, we have a minus here and a minus here, okay? So if I want to know what h is, okay, I know that x minus h is x minus 2, which tells me that h is going to be equal to what? 2 in this case, not negative 2, okay? Not negative 2. And how about k? K is equal to what? 3, not negative 3. We have x minus h, y minus k. And how about r? R is 16, right? That's right. I tried to pull one over on you. It's not 16, is it? R squared is what goes on the right side. So r squared is 16, which means that r is what? 4. All right, I couldn't pull one over on Chris. He's just too discerning. All right, so how do I graph it? Well, I'm going to go to the center, and then I'm going to draw some points. So first off, here's 1, 2. That's how I get to the x-coordinate, and then I go up 3, 1, 2, 3, to get to the y-coordinate, and here's where the center goes. Here's where the center goes. And now what I want to draw is the rest of the circle. So how do I do that? Well, what I'm going to do is I'm going to draw one radius, which the radius should be 4. The easiest way to draw a radius here, I'm not going to try to draw one diagonally. I'm going to try to draw a radius either to the right or to the left, or down or up, because that way it's going to be really easy to count how far to go. I need to go 1, 2, 3, 4, right? So the radius of my circle goes down to there. Okay, and now what do I need to do? What I need to do is draw the collection of all... Oh my god, this is going to be bad. The collection of all points... Oh, what if I just did this? This would be big brain. Okay. Wait, let's move this like that. Oh, yeah. There we go. Oh, it needs to be a little taller, doesn't it? Okay, wow, what an awesome circle. All right, so now I've drawn the circle. What do? I identify h, k, and r. I go to the center. The center should be at h, comma, k, which in this case was 2, 3. And then I draw one radius, which is 4. And then I draw all of the points, which are that far away from the center of the circle. All right, that's it for today. We'll finish talking about circles next time.